PA told to just plug in change in x for 1, where you normally put in 1, and then keep 0 here, but evaluate at sine 0, and then sine delta x, and then cosine 0, cosine. And then use that expression for the first position. Is that correct?
Not quite.
That's right. So why is the T telling them to do this? So when I'm doing...
You might have missed the square root of delta x. The answer is f0, this is f delta x, and then all multiplied by square root of delta x. Yeah.
And you can get that, you told me in the answer this morning that the transformation, I'm conflating the two. So I should just do the general case, something like this, where 0 to 1 xi plus 1, and then to that.
Okay.
Oh, okay.
And you'll get the answer right now.
Okay.
So the problem is that you can do the transformation on the integral, but then since you don't have, I mean, you can derive where the quadruple is coming from, which is why I suggested going back to that. There's a delta x in the quadruple that's not there because delta x is 1, so it disappears. So that's the extra factor that's not being taken into account. So what you should get from the transformation is delta x to the 3 halves power, and one thing,
From the transformation, right?
yeah, and then 1 over delta x is taken back out when you actually take one because it's actually being absorbed back in, and that gives you the square root of delta x. So I actually think
this should work, right?
yeah. So after trying to explain the quadrant rule and doing that, I actually think this is a little easier.
Okay. Okay.
Which is fine.
All right.
So I can tell it's midterms. I just posted the midterm review. You'll note that it is a little rougher than the homeworks are, and that's because we're not actually going to grade it. So it has a set of questions that could be asked on a homework, but also on the exam. So just to give you an idea of kind of the types of questions we might be looking for, it looks like this. These, I need to update Piazza. So these are just some guidelines for the midterm, so take a look at that. That's kind of what you'd expect for all of this, including the 10% reduction every hour if it's late. If you are going to be late, if you have like your 10 minutes over the deadline, probably talk to me. I understand that Wi-Fi goes down at the most inconvenient times. Try not to do that. If you go much more over that, I'm going to be unhappy. So, and if you do have any conflicts or anything like that, something happens, you break your leg unexpectedly because you're sitting and getting so excited about doing a midterm over the weekend, just let me know and we'll figure out alternatives for you. But this is what it looks like. There's some questions that vary in difficulty, and that is on purpose. But you should hopefully get an idea of kind of the types of questions we're going to be looking for. Some of them are very long. This one in particular can be a little bit of a pain. If I was to give you this particular question, find the first central difference approximation for the fourth derivative, we would probably give you some guidance as to how to solve the resulting system of equations, or just ask you to find the system of equations and not solve it because it is large. More of this type of thing is I'm kind of looking for you demonstrating that you know how to set these things up. and that you know how to use the tools that we've talked about and modify the tools and identify when those tools go wrong and how to get around that too. So if you have any questions, please feel free to discuss. There are solutions to all these things. We'll go over them on Thursday next week. And then again, the entire lecture on Thursday is devoted to answering questions, going over these. We probably won't have time to go through them all, which is why I give out solutions. But I'll probably go through some of the questions that I think are interesting. So be aware. But yeah, are there any questions about the midterm or anything else? Yeah. It's in the assignments. I think it should be on Courseworks at this point. So it's just like, it just looks like a regular assignment, except it has no grade. Any other questions? Yeah. Yes, the midterm is going to be available starting at midnight on a week from tomorrow. And due the Monday at 11:59, the Monday following. Technically, I think Simon is going to have office hours. That's always a kind of a tricky thing because obviously we can only answer questions one at a time, and we're not going to be answering questions. I actually haven't figured out how to turn off Campus Wire yet. So I will be watching like a hawk. However, make sure if you're going to post something on Campus Wire, you do it to me and the TAs only. Otherwise, I will delete your question as fast as I can. We will answer questions like, if you get stuck on a coding problem, and it is purely a coding problem, we will probably help you out. But we're just going to be answering clarifying questions. So, any other questions? Yeah. If there is something generic in there, yes. If it's a clarifying piece of it, yes, for sure. Any other questions? All right. Close this real quick. Okay. So again, just to waylay any fears, the next material is going to be on the final, but not on the midterm. So enjoy this. There will be homework available after the midterm on this material as well. So you will get practice at it. So we're going to continue kind of on this idea that we're approximating things from calculus. And there's two parts to this these ideas. But basically, we want to solve numerically ordinary differential equations. And in this case, we're talking about initial value problems. We eventually will start talking at the end of the semester about boundary value problems. If you're more interested in those types of problems, the second course in the sequence, which is numerical methods for PDEs, we go right into boundary value problems right off the bat. So that's kind of the continuation of those ideas. The difference between initial value problems and boundary value problems are that an initial value problem is something that we usually think about at a time. We have data. We need to have some initial conditions. And usually we think about those initial conditions being, again, at like time t equals 0 or some beginning time. All the data is at that particular time. Whereas a boundary value problem, we usually think of those as being in space. And you have a boundary value on each side of the domain. Say x is going from 0 to 1. You'd have a boundary value at 0 and a boundary value at 1. And those tend to be second order ODEs, so two derivatives, which should be suggestive on the homework for today. So let's get started. So we're going to look at these things as systems of ODEs, primarily because that's a very generic idea. Any higher derivatives in an ODE, so you say you have a second order ODE, you have second derivatives, you could always rewrite those as a system of first order ODEs. And so everything we're going to talk about is assuming you have transformed your ODEs into a system of first order ODEs. So we only have one derivative to worry about. It could be in a system, and even a nonlinear system, but we're going to approach it from that standpoint. So here's just the general notation. We have some unknown vector, u, which is an unknown function, set of functions, and we have a right-hand side, f, which is also could be a vector if u is a vector, and it's a function of t and u. If the t is not in there, then we call these things autonomous. And we also need this initial condition. Generally, we're going to just label those as U0. They could be all sorts of different things as well. The fact that the initial time is at t equals 0 is completely generic. You can, of course, start at any time you want. But just to kind of make this so it's a little simpler, we're going to assume that that's the case. Okay. So this is the generic setting we're in. There's lots of good examples, and so we're going to go through some of these, and we're going to use them time and time again just to explore some of the methods. This is kind of the simplest of the non-trivial ODEs, and that's where U is representing a concentration. So in this case, maybe radioactive particle concentrations. And we say this particular radioactive particle concentration is decaying at some rate lambda. So this is a little bit of a, you'd be a little bit careful about this. Here I'm actually assuming, in this case, lambda is positive, but really you could absorb the negative sign into the lambda here. The important part is that the concentration is decaying. That's what that negative sign is saying. The derivative is going to be negative. But it's also dependent on, of course, the amount of stuff. So as the concentration goes down, the decay also goes down. We can solve this given our initial condition C0, and it's just the exponential function. All right, C naught e to the negative lambda t. This plotting is fun, and we're going to do this a bunch of times. Pull this up a little bit more. Okay. So we have something like this. These are for our actual numbers. So we have some concentrations that are normalized to 1 at time t equals 0. And in this case, over 1,600 years, which is going to be the lifetime of this particular particle, it goes to half of its original concentration. Okay? So very simple ODE. We know it's decaying. We want to make sure that whatever numerical method we're going to talk about is also going to have this particular type of behavior. And we'll see that that's actually not a trivial thing to do, even for a simple ODE like this. Not to be outdone, we can make this as complicated as we want. So something that chemists and other people dealing with chemistry do all the time are just very complex. I mean, this isn't really, honestly, that complex. You can have hundreds of concentrations of species of chemicals or particles, and they can have complex inputs and outputs, and one decays into another, or two decay into one. You can express this in a continuous manner using a system of ODEs. So in this case, this is a system. The U vector is going to be C1, C2, and C3. And then the right-hand side function is going to be negative lambda 1, C1. So C1 is going to be decaying at the rate negative lambda 1. In this case, C1 is decaying into C2. That's why this actually has the exact same thing without the sign on it. So stuff is changing C1 to C2, and C2 is decaying into C3 at lambda 2, the rate lambda 2, and then C3 is just decaying in this case. Oh, that should be C3. That's typo. Okay. So a very simple kind of cascade of concentrations that we have. So here it's written as a system. This is a linear system of ODEs in this case. So again, U is going to be C1, C2, C3. The time derivative is on all of those. And that's going to be equal to this matrix A, which has the lambdas in it, times the vector U again, or the C1, C2, C3s. So if you actually multiply all this out, you'll get the exact set of system that we had before. And the matrix has various properties to it. It's upper triangular, so that has some implications of what's going on. But the general solution to a system of linear ODEs is this thing. So this is the vector of initial conditions times e to the AT. So A is a matrix still. So this matrix exponential idea that's not something we usually talk about too much, even in an ODE class. But there's lots of ways to compute that. So this is the kind of the generic way to think about what is it that we're doing here. One thing that often is done as well is actually to take and flip the EAT with the U0 so that it would be, so whatever this thing is, it's going to be something looking like a matrix, and then you might get the U0s back out of it. by multiplying it by that. So you can actually see eventually that this is going to again, collapse down into just an exponential dependent on various parameters. The other thing here I do want to point out, and we'll talk about this later, much later, I believe. This matrix exponential can be written as a Taylor series. And if you actually write this as the Taylor series of the exponential, you can kind of see, well, this is going to be various powers of a, right? Because you're just going to be sticking a times t inside of each of the powers as you go up. And so, though it's an infinite series, that's an easy way to think about approximating this, what we call a solution operator. And as you take more powers of a, that's actually going to amplify certain eigenvalues of the matrix A, which is where we're going to actually see this again. Computing eigenvalues quickly and actually caring about what are the largest eigenvalues, because those are going to be the ones that are going to affect this the most. It's going to be the ones that are. So lots of stuff to look forward to. So that's a linear system. We can talk about particle tracking. So if you wanted to, in a Lagrangian sense, have a particle, it has a position, and then that particle, of course, take the derivative of its position, you should get out the velocity. So this is a very common thing to do as well. We have positions, we have velocities, maybe the velocity field is given, and then this is just an integration. But you also are probably going to have velocity fields that are dependent on the position of the particle, because maybe it's changing spatially and in time. So this turns into a system of ODEs as well, and something we can actually also kind of analyze. So this is actually getting more towards the dynamical systems part. So those of you in dynamical systems, you're going to see some of these analogs popping up even in the analysis. It's not required that you know dynamical systems, but there is some interesting connections there. So now to a little bit more of an interesting case. This is the van der Pol oscillator. It is nonlinear. It's weakly nonlinear. We have y double prime minus mu times 1 minus y squared times y prime plus y. So this is an oscillator, and the key to this oscillator is that the dampening of the oscillator is dependent on y, the displacement of the oscillator itself. So that's that mu times 1 minus y squared part. So there's all sorts of interesting things that happen with this. This is kind of one of the simpler, interesting manifold problems. We have to have two initial conditions. Right? We have to y0, so the initial position of the oscillator, as well as its initial velocity. That's the y prime part. And we can write this as a system of equations like this. So I allow y and y prime to be u1 and u2. And then I can write the resulting system like I have here. Okay? This is something you're going to be expected to be able to do, which is why I want you to try to do this. So this is the answer. Convince yourself that this is really the same thing as that. Okay? And talk with your neighbor, make sure you're all on the same page. And I'll do it really quickly and kind of talk through the generic way to do this. But try it out with this and see if you can figure out how to go from this thing, identifying the new vector u, and then getting back to this right-hand side function f. Okay? So I'll give you a couple of minutes for that. All right, hopefully you've at least had some time to think about this. But let's go through this. So I've kind of told you exactly how to identify the new vector of u. This is very generic. Basically, whenever you have a single ODE, but it has higher derivatives, and you want to turn it into a system, the first thing to do is to take and identify the derivatives just like this. So you have u1 is going to be always y, and then u2 is going to be y prime. And you only have to do up to all but the last derivative, okay? Because that's all you need to represent. One way to check to make sure you're kind of guessing how long this vector has to be, you have two unknowns, functions, u1 and u2, and I have two initial conditions. Right, so you should have only that many things, because each of these are going to, of course, be the initial condition on u1 and the initial condition on u2. So you need to have that match, otherwise we're all in trouble. Okay? So what we do is we say, okay, this is the vector I want, and I've identified their values. I go back to the original equation, and I say I'm going to replace these things with u1s and u2s. Okay? So some of these are easy. We know what y is. That's u1. We know what y prime is. That's u2. u2. 1 minus u1 squared times mu. But I don't have y double prime. Okay, so that's a little problematic. What we do, and this is why we left out y double prime, is we recall that what we're actually doing is we want something that has a derivative of our unknown vector u. So here, what those things are, is here. So we have d dt of u1, u2. That's equal to the identification of the unknowns, y and y prime. If I take the derivative of that thing, I just do it for every value entry into the vector. So this is going to be y prime, y double prime. Okay. So now we have this, and we need to figure out what f is. Okay, so I know what y prime is. It's u2. Right? That's by definition. So this first one is going to be u2. So that's why we get that. And in fact, when you're kind of doing this, you're going to find that all of the entries, except for the last one, when we're eventually writing it as a system and we have this right-hand function, everything above here is going to have u1 and u2, or u3 or u4. Okay? It's only the last one that's going to be more complicated, because we still need to specify y double prime. Well, we didn't specify it up here, but note we have y double prime. If we move all the rest of this business onto the right-hand side of the function, we get y double prime is equal to this stuff. All right? And if you note, this is what's in here. I feel like I'm missing a minus sign. So let's do this. We have that expression. So I have another typo in there. All right. So then I just have to go here, and this is just the last piece of our right-hand side vector, and that's negative mu times 1 minus u1 squared times u2 minus u1. Okay. Yeah. Oh, that's why, okay. Not a typo. This is the typo. There we go. Thank you. Does it look good now? All right, okay. So it's just a little bit of algebra really is what's going on. Sometimes you have to be a little bit careful. You do need to actually isolate y double prime here. And if this is actually going to be a highly nonlinear ODE, which can completely happen, this can be a little bit more challenging. And in those cases, you have to be careful. But we're not going to address that at all. We're always going to assume that we can write our ODE in this type of form. Okay. So we've rewritten our ODE, and we want to solve it. So I just actually want to give a little bit of a demo on SciPy.integrate's ability to do this stuff. We're actually going to be implementing a lot of these algorithms it's going to use. But if you want to just integrate an ODE, this SciPy.integrate functionality does allow that for you. So just starting out here, we have f. So I'm defining f here and giving it a generic mu, that coefficient that we had, parameter. And you can see that all f is going to be doing is returning some right-hand side function. It gives you a t, if you need it, and a u. So u is going to be the values. And all these ODE integrators are going to take is an ability to actually evaluate f. That's all it's asking you to do. So oftentimes you say, here's my right-hand side function, here's my initial condition, integrate to whatever time I want. That's what their job is to do. But we do need to implement this f. So we have u1 here. So note we're counting from 0. So this is really u2 up above here. And then we have our implementation of this. So we have that. Here's our initial conditions. So I'm creating this big vector u, which is going to contain all of our solution. And of course, the first piece of the solution is going to be the initial condition. So that's where I'm storing it. Here I'm indexing such that the first index is going to be either u1 or u2, or u0 or u1. And the second index is going to be the time index. So as that 0, so the next point that I would be evaluating at would be u colon comma 1, like that. Okay. So now we're actually going to do all of the implementation here. So the way the SciPy.integrate works is we construct an integrator. Okay. So that's creating what I'm calling an integrator. And at the beginning of this, you have to give it that function f. So it's going to figure out how to evaluate that. The next thing we have to tell it is to use what algorithm. So for those of you from MATLAB, if you want to use Runge-Kutta 4.5, RK4.5, that's the same thing, or roughly the same thing as Dupree 5. Dupree is one of the people who are responsible for that. So that's just telling it what algorithm to use. And then the last thing we have to actually tell this integrator, because it keeps track of this, is what the initial value is. And we stored that in u colon 0, like that. Okay? And now we're ready to integrate. Okay? So in this case, you can kind of just tell the integrator to integrate to some time you want. But I want to kind of see the integration in time. I want to see the time trace, so the actual solution in time. So I'm going to ask it to do, let's do this. Did I already call t? Let's say t range. Probably going to screw something up. Okay, so I've already said I want the range from 0 to 100, and I want to do capital N evaluation. So that's just going to give me an output 500 times between the time value 0 to 100. So this is completely arbitrary. I'm just going to use that as how I'm going to plot this stuff. So each time I want this to integrate, we say integrator integrate, a little bit of a mouthful, to the time that I want. And it can fail, so we're going to make sure that it doesn't. So we ask it if it was successful. And if it wasn't, we break, and we can handle that. If not, we're going to put the new solution into u. And unfortunately, in a cruel twist of notation, they use y for this internal representation of the solution at that particular time. So if you actually ask the integrator to integrate to a new time, it wouldn't keep the old time value. So that's why we have to grab it and tell it to integrate to the next time. And the integrator is also keeping track of a time as well. So this is a little bit, we'll see when we actually implement our own methods how we're going to do it. It's a little bit simpler, but there's a lot of hidden things going on in the background here, unfortunately. But it does work. Okay, so I need to do this. think that's it. That is not it. Let's see what happens. Oh. There we go. So that's the solution with mu equals 5. It is a really strange oscillator. If you remember, the solution to an oscillator should be kind of a nice sinusoidal varying type of curve. This has some sharpness to it, and it has to do with the fact this is nonlinear. So you can play around with this, change mu and things like that. There's also kind of an interesting phase diagram to this thing. It has sharp edges, and it seems like in terms of, this is the initial condition right in the middle here, and then it kind of circles out and then finds this manifold that is pretty stable. So it's just going to oscillate around this thing in phase space. So this is, just to be clear, this is yt, and this is y prime of t. Okay? So those of you from dynamical systems probably have seen things like this. This is probably not the most nice limit cycle that you'd want to see, but you can prove all sorts of things about this. But there is one thing I want to point out, and that's that we're using 500 points. We can increase this to 1,000. And we'll see, actually, we get rid of some of those stuff. So this is just getting at the idea that you got to be a little careful when you're numerically doing anything. From the last picture, 500 seemed like a lot of points. But you can see if I use 1,000 instead, so I'm just taking snapshots of the solution more often, we clearly see that this is probably a limit cycle. It has these sharp edges to it, which is interesting. But we don't see that kind of weird disassociation of those curves. Okay, so this manifold, I would say, is pretty clearly a limit cycle. You can go the other direction, and it becomes even more clear that this is questionable, because now I can't even tell what's going on. All right? So the key here is that the integrator is probably doing the right thing. It's just that when we're actually viewing this thing, we can't actually see what's going on. The other way you can actually look at this is, instead of plotting just the line, it's actually probably better to do dots. So, I don't know what that means, but that's with only 100. If we up this to 500, what we had before, you can kind of see that, that's probably actually a limit cycle. And you can also see where we seem to be skipping over parts of that limit cycle, and that's just because it's just moving through phase space fast enough at those points in the limit cycle that we're just not capturing it. And this is completely random in terms of how we're doing that. And then just to close the loop on this, we do 1,000. You can kind of see, it's like, well, maybe those weren't such hard edges. Maybe it's because I actually just am not actually evaluating the entirety of the limit cycle. We expect this to be continuous. You can't be jumping around in the phase space like this. That's not possible unless you're doing maps. So it's probably a good assumption that these things are connected, but we're clearly not getting at those types of dynamics. So this is just a word of warning about using these things. Numerics are always a little bit difficult, and you should not necessarily distrust them, but just be aware that there are issues. Okay. So let's actually talk about numerical methods. We're going to introduce a bunch of new notation. It's kind of new, not really, but so T0 is going to be equal to 0, and we're just always going to basically assume that for the most part. We're going to, instead of talking about delta x's like we were in the past, we're going to talk about delta t. That's just the difference between T0 and T1, for instance. So this shouldn't be too surprising. But this relationship where we're counting from T0 some n time steps into the future, we will be using this quite a bit in the sense that we want to move forward into the future a certain number of time steps. We did this occasionally with delta x, but you could choose either boundary when you're talking about space and time. This is much more natural to talk about. We also are going to stick to the notation that U0 is going to be, little u0 is going to be the exact solution evaluated at the corresponding time index. Okay, so little u, T0 is the true solution, and we're going to approximate it with our capital U's with the same index. Okay, so notationally, little u is the true solution, big U is the approximation. Okay, so we talked about finite differences. Well, we have a derivative. It is a natural thing to do, is to take a finite difference and use it to approximate that derivative on the left-hand side. Okay, here we go. This is a forward difference. All right, we're looking forward in time, delta t, subtracting off ut and delta t. So right now what I'm doing, I'm just actually plugging in the true solution here. So whatever I'm doing, this is going to be an approximation for the next time, t plus delta t. Okay? But note that that's just one part of this. I've discretized the derivative, or find some approximation to the derivative. But I still have f kind of lurking in here. Right? Where do I evaluate f? So one thing could be I could evaluate f at t, so t0, for instance. Or I could evaluate it at t plus delta t. That seems like a natural thing to do as well. Okay? So these types of decisions bring up how broad of how many different types of ways to go about doing this there are, and there are lots. One way to actually look at this problem is to actually just do integration and do a quadrature rule. If we take the integral of both sides of the original equation, so du dt is equal to f, and I integrate from t to t plus delta t, so that's why we have t tilde everywhere. I do that on both sides. This is the fundamental theorem of calculus. I get ut plus delta t minus ut. Okay, so that's just on the left-hand side. That's exact. But now I'm going to actually approximate this side with a quadrature rule. And in this case, I'm using the left-hand rule. Right? Just evaluating the integrand, multiplying by delta t, evaluating the integrand at the left-hand side, which in this case is just t. Okay? So we know that's first order, that quadrature rule. And in fact, this is actually going to turn out to be a first order method for solving this. Okay. So this is a little bit more specific to quadrature, or to O to E's, because we do have a u over here. We did need to specify that. But we're saying because u is actually evaluated at t as well, that we can do this in general. Okay, so we have that. Well, let's actually just write this as a numerical method. So here we can rewrite our scheme. So now we're going to say, the equal sign is probably not so great here, but we're going to translate this back into something that looks like a discretization, a finite difference discretization on the left-hand side, and f is going to be evaluated at tn. So this t turns into tn, some generic t in the future, and I want to get to tn plus 1, and I'm evaluating f at tn un. Well, I have a frog in my throat. And then I can actually just rewrite this. The nice thing about going from here to here is that we can see how going forward into the future, un is going to be updated by delta t times f, and that's going to give me un plus 1. So assumedly we know what un is, because we're going to start at an initial condition. So the first u is going to be u0 at some time, and then that's going to give me u1. Using u1, I can find u2, and so on and so forth. So we can march forward in time directly that way. This is called forward Euler, and it was featured in a particular NASA movie rather recently called Hidden Figures. This is how they figured out how to go around the moon, supposedly. Actually, they used something much more complicated than forward Euler, but it basically has the same type of idea to it. And they did it by hand, which is a little crazy to me. But this is the first kind of most basic method that we can use. All right, so we have our method. So what's this really look like? Well, one way to kind of look at this is using this figure. So what we're doing, we're going to say we're at t equals 0. We have on the left hand, again, this is the true solution to our O to E in this case. So this is just doing radioactive decay again. And what I'm actually saying is I'm going to pick a delta t to go forward into the future. And I'm going to say approximate the derivative of u, because that's really what f is specifying. That's another way to look at it, O to E. You have du dt is equal to f. So f is actually a first derivative of u. It's the representation of the first derivative of u. We're evaluating that at 0. So this line, which represents the derivative, is centered and touches the curve, at least in this case, up there. And then as delta t gets bigger and bigger, you see we diverge from the curve. So in this case, this is actually going to be our new solution if we took delta t this big. And then this would be our error. Okay. So there's lots of things we can actually analyze here. This is clearly just approximating the derivative at a point. And we see that we expect to actually underestimate in this case. And this is actually a generic thing. We could pick all sorts of lambdas. We're always going to underestimate the true solution in these particular test cases. Okay. So let's actually just find this thing. So I'm going to let you have a couple minutes to try to program this up. And then we'll come together and do it as well. And you should be able to see that you're actually going to find that the solution is actually decaying faster than it should be. So basically, the particles, our concentration is actually going down faster than we expect it to, actually. All right? So give that a whirl. We'll come together, we'll program it up. Lots of things I want to say about this particular thing because we're going to do it a lot, basically copying, pasting, and then changing basically our stencil. And then we'll try to figure out some conclusions based on that. So I'll give you a couple minutes for that, and we'll move forward from there. Okay. So there's lots of stuff here. Right-hand side function, the decay constant I'm calculating so that I have exactly the half-life specified at 1,600 years. And then we have the initial condition at 1. So first off, we need to set our initial condition. Oops. So U Euler 0 is going to be the initial condition. And from here, we can, oh, I did it again. I'm going to do T. I don't like Tn. N enumerates T Euler. And because, again, we've actually already done the first one, we're going to do that. Oh, that's interesting. I feel like that should be the right thing. I think there's a mistake in the notes. Okay, so I want to do, T is going to contain what Tn is, the current n index into the array. Euler, if I could spell, so the nth value here, or the n plus 1 value, oh, that's why I did that. Well, we'll try this. So n plus 1 is going to be equal to the last step, or the current step, plus delta t times a function evaluation at tn and un. That, I'm a little worried because I actually might be outthinking myself. Oh, no, that works. Okay, so we get that. So you can see this isn't actually super complicated code. And we're not even taking, we're taking pretty good substeps. I mean, if these are years, you know, what is delta t? I don't know. Large, it's 100, on the order of like 100 or 200 years. So you can see just gradually that these red dots are actually going below the line, which is exactly what we expected from this picture. If I take bigger time steps, in other words, oh yeah, so that's exactly, it's 160 years. If I take, say, 5 time steps, you can see the error actually increases per time step like we expect. Okay? And of course, you can go the other direction. If you take more time steps, as delta t goes to 0, we expect this thing to converge to the true solution, so we can test that out. 50. You can see, yeah, it's right on top of the curve. You actually can just barely see that it still is getting a little bit less than the curve. But this is just representing the convergence in the error. That. Okay, so oops, let's get that. Okay, so we can kind of play with this all we want. We know that there was a second order finite difference, and that was the center difference that was missing the middle point. So we can use that to approximate the derivative as well. So here I put this on the left-hand side, and I'm going to continue to evaluate this at that un. Okay? So this is a little weird. We have un plus 1 and un minus 1 used for the derivative, and f is being evaluated at that missing point, un. Okay? This is commonly known as leapfrog, and it's because it's leapfrogging that middle point. That's where the name comes from. Very, very popular to use in like atmospheric dynamics, or it used to be anyways. There's lots of issues with using this that we will actually come to a little bit. The other thing too is if you notice that the last one was only dependent on un to get un plus 1. Here we're seeing we're dependent on un and un minus 1. And we distinguish these two cases by saying this is a multi-step method. We have to use multiple steps from the past or the future to get the new step, whereas forward Euler only needs un. So it's a one-step method. And there's reasons why you might want to use methods one way or the other. So what's the leapfrog look like? Well, if you look at this, this is more like a secant approximation to the derivative. So that's exactly what we're going to see. So it's using un minus 1 and un plus 1, and it's actually creating a derivative between the two, dependent on delta t, to approximate the derivative in the middle, which is going to be a closer approximation to that derivative, is basically what we can see. Okay, so let's see what happens. I'll just code this one up real quick. You leapfrog 0 is C0. But no, we have a problem now. What's my problem? I'll let you think about it. Let's actually code up this loop first. So here's a different way to actually code this loop up. So you leapfrog. And here I actually have to solve for the n plus 1 term. So here I've just done that for us. Okay. So that's the update, just based on this formula right here, solving for un plus 1. What's wrong with this? Where am I going to go and get into trouble? Yes, so because it's a multi-step method, the problem with multi-step methods, you got to get them going. Right? If I actually plug in, I don't know U1, right? I haven't actually specified what that is yet, but if I go into this formula here, n minus 1, if I plug in 1 into that, that's not going to work very well. In fact, the way I've indexed this, it might actually look like I could use this, but I have to be very careful because I don't know what UN is for the current step. All right? So I'm missing data is basically the thing. I need to get this thing started so that I can actually find it. So the first point that I actually can use Leapfrog for is not 1, it's U at T2 in order to get all of the values that I want. So we can modify this a little bit. Because we know of a method that can do this. So we're going to use that to bootstrap the method. It's called bootstrapping. Okay, and I'm going to use forward Euler for that first approximation, because I only need the initial condition for that one. Okay, well, that's good. Here, the indexing actually is fine, I think. Nope. What did I do? Oops. Wait, what? No, I just accidentally Wait, I'm very confused. Oh, it is this one. I see what you're saying. The dot shape. Oh, yes. Thanks. I was confusing myself. Okay. Leapfrog. I mean, let's actually decrease the number of steps here. Oops, not that one. Leapfrog is pretty good. Not that there isn't any of this decay business going on. In fact, it's almost on top of the line. Now, again, we not necessarily expect this to happen, but we also can show that, like our second order approximation to the derivative, this is going to converge faster than the first method, even if we're using forward Euler for that first part. We are committing an error there, and we're always going to be kind of beholden to that error. And we're going to talk at length about what to expect from an error that you commit and how it grows or shrinks in time when you're stepping forward, because that's actually really, really important. But for right now, this looks great. Until I changed this a little bit, and you can see I actually ran this already. I've changed some of the parameters, just made them smaller, and we'll talk about what I did. But clearly, this is horrible. This is not approximating the true solution anymore. It's amusing, but it's just not working. And this is very common for Leapfrog, this type of error. And these are, no matter how many points I put in here, you can see that there's this, basically saw pattern. So it is going to be jumping up and down like this. And this is what we call an instability in the ODE solver. It's going to eventually blow up, even though the solution is not. Okay, so this is going to continue to grow if we keep on going on time. So it's not great. We can increase the number of points, and you can see it actually is going down. So in principle, you'll be okay. The other interesting thing here is that these do really look like they're on either side of the actual true solution. So if you average every other, you probably will get a fairly good approximation. But that's in a particular case, in this case. So if the solution was actually doing something more complicated, we'd be in trouble still. But keep this in the back of your mind. We're going to actually address exactly why this is happening a little bit later. Doing over time. All right. So we also we had forward Euler, and we made a choice that we're going to evaluate f at the left hand. When we're arguing that this is a quadrature rule. But there's also the right-hand rule for quadrature. And that gives us something that looks like forward Euler, but it's called backward Euler. And it's because instead of evaluating f at tn and un, we're evaluating it at tn plus 1 and un plus 1. Okay? That's the only difference. However, there's an important problem here, and that's that f now contains something we don't know. Right? We know what f is, but we can't just evaluate this and update un plus 1 because it has a un plus 1 on the right-hand side. So what do we do? Oh, and so when we have these types of things where f is a dependent on un plus 1, we usually call these implicit methods, and in contrast to explicit methods, which forward Euler and leapfrog are. Basically, it just comes down to the fact that it's implicit in the sense that f is containing a un plus 1, like that. Oops. See if it's better over here. I don't know why sometimes the slides actually do not have problems with that. I've never figured out what causes that. Anyway, so here's where we can go. We have un plus 1 equals un plus delta t f. If we plug in what f is in our simplified version, we see that it's lambda times un plus 1. And we can solve for un plus 1 by doing some algebra. So just subtracting off delta t lambda un plus 1 to the left-hand side, divide through, and we get this. So this is the new update formula for this particular function f. You can't always do this, unfortunately, but we can in this case. It works well. So there's lots of things. Let's see if this actually shows. Is that the part that's? No. So there's lots of things to note about this. One is we know that delta t is going to be positive. It doesn't make sense to have something that's negative, that's a distance. We also, the way I've defined this, lambda is going to be negative for a particular problem, for decay, which means that the bottom of that, the fraction there, the denominator, is going to be greater than 1, which means that the value on the right-hand side is always going to cause the thing to get smaller. So as un marches on, we're always multiplying by something that's larger, or excuse me, smaller than 1, which means going from un to un plus 1 is always decaying. Okay? So similar to forward Euler, where we saw it decay faster, this thing is actually going to have a similar behavior, but the opposite, which is interesting. So I'm going to skip that right there. But this is basically the idea. The derivative is going to be evaluated based on the future version of it, so the un plus 1, and we're just solving for it in this case. So in this particular kind of test case, where we're actually going to expect to overpredict what's going on, dependent on delta t. This one works. So you can kind of play with this all you want, even in the case where you have a system of ODEs, but as long as that's still a linear system, so like the chemical system of equations we had before, you get an A out, being a little bit more careful, because you can't just divide through by a matrix. You can rewrite this thing, move everything over to the left-hand side, factor out u. Capital U is now a vector, which is why we get the identity minus a times delta t. And then we see the actual solution is going to be the inverse of whatever that matrix looks like. So it's basically the inverse of the original matrix A, but it's 1 minus delta t times that thing. Oftentimes, again, we'd be interested in what the eigenvalues of that matrix A would be, and that, of course, comes into what that thing is doing. But we can still do this, right? We just have to invert that new matrix. So this is with the linear systems. If for arbitrary f, which is interesting things to solve that you can't do by hand, often we have complicated f's, and we can't do it. So we have to use something else. A lot of times that could be Newton's method. So you can actually put into this Newton's method where you're solving basically the root. So you're basically doing this, but using it algorithmically. And so we will actually investigate kind of the combination of something like Newton's method or something similar and an ODE solver to see kind of how that works and when it doesn't, because as you can imagine, that gets complicated. All right. So here again, we have backwards Euler. We're just going to implement this real quick. So we have backwards 0, is equal to C0, just like before. Then we have for n in range. So probably the trickiest part about this is I'm indexing this in a particular way. Just indexing past the end of an array. Just play with it, try to figure out where things are going so that you can index into this properly. So I tried to actually use a bunch of different methods just so you have some ways to actually do the indexing if you find a way that works best for you. So from our little algebra thing over here, we just basically want to do this. So that was n divided by 1 plus decay constant. So this is 1 plus it because the decay constant is actually positive. I've already factored out the negative sign, perhaps annoyingly. Okay, so we get that. And as you can see, well, backwards Euler actually seems to be doing exactly what we expected, and it's actually overestimating the solution value. We can see it a little bit easier if we change this. 5, you can see it's increasing as well. So basically, just the opposite of what forward Euler is doing in these cases. Okay, are there any questions so far on this stuff? This is basically just throwing you at a bunch of methods, and we're going to come back to analyzing each of them. In these cases, these are easy cases. Usually we can't actually say that for sure. It depends on the problem. In these cases, that's a generic statement. Backward Euler is always going to overestimate. Forward Euler is going to underestimate. Leapfrog, if it works, will be kind of take the best of both of those worlds. Yeah. So actually, that's a good point. If you recall, one of the ways to get the second order finite difference was to take the average of the forward and backward differences, which is exactly what we're doing. So to correct that error, as we saw, if we took the average of the oscillations that we're seeing, it actually gave us a really good solution again. And that's where that's actually coming from, why that actually is the case. Okay. So another implicit method is called trapezoid, trapezoidal method. Sometimes this is also referred to as midpoint. Slightly different, I would say. But of course, it is related to the quadrature rule with the same name. As you can see on the right-hand side, that is going to be basically the same trapezoidal rule that we're familiar with. If you multiply by delta t on this side, it is exactly the trapezoid rule for one partition. And we can see we have un plus 1 minus un. Okay? So that looks like, on the left-hand side, like forward Euler. That's a first-order approximation to the derivative. But in this case, actually, because we're evaluating the function at 2 values, we do get second-order accurate convergence. So it's not just based, you can't just say, oh, I used a second-order or a first-order derivative to approximate the derivative. It also has a lot to do with where you're evaluating the function as well. So lots of variations in these things come up. Actually, almost missed my question. Okay, so I did this for the last scheme. I want you to try to actually figure out for the kind of canonical example we're doing. So f of t in u is going to be equal to negative lambda u. Okay, for that problem, try to find the update formula. So get this thing to be in the form un plus 1 is equal to stuff. Okay. So you're going to have to do some algebra, some plugging in. So we'll do that. I'll give you a couple of minutes for that. And then we'll implement it and probably be done for today. So discuss with your neighbors. Don't be so quiet. This is going to come up a bunch of times. Always, as usual, always try to do as much math on paper and pencil before you stick it into a numerical algorithm. Because if you kind of just charge on forward and you actually try to do something much more complicated to get this f to not have a un plus 1 in it, say Newton's method, you could be shooting yourself in the foot. It can be bad. So another message for the day, I guess. But anyway, I'm going to give you a couple minutes for that, and then we'll come back together and code it up. I just did. All right, so if we just plug in, I'm going to use lambda u, so this would be in the general case for any lambda. Things first, we can actually just solve for un plus 1, at least the un plus 1 that's easy to solve for. So we get un plus 1 is equal to un plus delta t over 2. And let's plug in what f is. So we get lambda un plus lambda un plus 1. Okay. We can leave the un on the right-hand side of the equation. That's fine. But we do want to move the un plus 1 onto the left-hand side. And so can we write this, factoring out the un plus 1 right away, as 1 minus delta t times lambda over 2. Okay. So that's taking lambda un plus 1 and making sure to take this with us. And the right-hand side, I actually get un times 1 plus delta t lambda divided by 2. Okay. And now we just divide through by this thing. So this looks like backward Euler to some extent, except now I have this division by 2, and I also have this term in the numerator. We can actually make the same arguments. We do know that the ratio of these two things is always going to make, in this case, for the sign on lambda, it's for the thing to decay, which is what we want. But the actual update formula then is going to be un plus 1 is equal to un times 1 plus delta t times lambda over 2 over 1 minus delta t lambda over 2. Like that. Okay. So in this case, actually, we can pre-compute this. We don't need to compute this every time, and that's how I'm going to implement this. But you should be starting to see some common kind of things that are happening here. In particular, oftentimes we're going to have delta t times lambda, and that value is actually going to be very important, it turns out, for how these things actually work. So we have that. Check my math. I think I'm good. And then let's actually implement this. Go down a little bit here. Okay, so I'm going to go back to what I was doing before. So note, this is actually still a one-step method, so we don't have to bootstrap it or anything like that. Here I'm going to do int constant. So this is the integration constant that I'm going to use every time. So unfortunately, I did not put the negative sign of the decay. You know what? Let's just do that. We'll just put that here. Hopefully that doesn't break anything. There we go. I think that'll work. Delta t divided by 2. 1 minus decay constant minus delta t divided by 2. Like that. Okay, so, and now I have my primary loop. Okay, so we have u is going to be equal to un plus 1 n times the dat decay constant. What just happened? Probably blowing up. Oh, thank you. Too many constants running around. There we go. Okay. So actually, this looks very nice. We can analyze this. This is second order, similar to leapfrog. In general, of course, we can't just solve for un plus 1 out of f, but this is a great method if you can. And you can, of course, formulate a way to get around that as well, which brings us to solving systems of equations again, which we will go into later. So I think this is a good time to stop. The next topic is error analysis. So we've done a bunch of stuff. We have some ideas, but now we're going to show that what our ideas were correct. And then we'll finish out this, at least part 1 of this lecture, looking at some additional different methods that are fairly popular as well. So have a good weekend. I will be on Campus Wire hopefully as late as I can tonight for the homework. Try not to send me panicked emails at 11 o'clock at night. I probably will be sleepy. So you'll get me answering when sleepy, which is maybe not a good thing. But anyway, have a good weekend. I'll see you Tuesday. No, but you can look at the documentation. It explains it. It's complicated. I mean, it's changing delta t. It's using different types of methods. All sorts of logic.
So I think for like sci-fi, are we expected to learn the sci-fi? Like just something.
I'm just showing you.